All right, let's look at simplifying radicals here today. And a radical is what looks like something like we think of it as a square root symbol, but it doesn't have to be a square root. Sometimes it looks like this and has a cube root, or maybe it's a fourth root or a fifth root. Today we're just going to look at square roots and cube roots. We have to start by thinking about where those come from. And so when you think of a square root, we're going to start with that. If I multiply two things together, and that's the same as squaring them. So that'd be like a 4 squared right there. All right, that I know is a 16. Now what we're doing is the opposite of that. The opposite of squaring, or the inverse of that, is to square root it. So what I do is I take this number right here, and I would put a square root over it. And what this is indicating, what that square root indicates, is what is the number that you could square to get 16. So really I'm looking up here and saying, oh, well that would be 4. So the square root of 16 is just 4. All right, now this can get way fancier than that. So let's try some other things. What if maybe I did 5x times 5x? All right, so when I multiply 5 times 5, I get 25. And x times x is x squared. So what we're really going to look at, now I'm kind of building it up to that, what you're going to see on your homework is the square root of 25x squared. And so what you're having to do is, in your mind, you're going back and thinking, what were the two things that or what is the one thing I would have squared to get that? And so the answer there is 5x. All right. You might even see it with something like this. Let's say you have 2 times 2 times 2. Well, 2 times 2 times 2 is, well, we could think of it as 2 cubed, but it's really just 8. Not 6. 2 times 2 is 4, times 2 is 8. All right, so what you're going to see then is the cube root of 8, and so what you have to think of is, what is the number that I would have cubed? Oh, I would have cubed a 2, and so that's my answer. All right, so now I'm kind of done doing all of this stuff up here. I'm not going to do that. You just have to recognize when you see the square root, you're looking for what's the number that you would have squared to get that. All right, so we have some what we call perfect squares, and we have perfect cubes. These are all the numbers that would square nicely, that there is something that it would square root and come out cleanly on. So I'm going to do some different types of problems, both with square roots and with cube roots. And we'll kind of gradually get harder and harder with some different problems. Okay, so what about, I'm just going to do several examples. Let's say you had the square root of 36x squared. Okay, the square root of 36 is 6. And the square root of x squared is just x. So my final answer is 6x. Okay, we could make this fancier. What if I did the square root of, let's do, I don't know, let's get really fancy. 9x to the 10th, y to the 12th. All right, the number part's the easy part. The square root of 9, that's just a 3. And then x to the 10th. You have to think about what that would have looked like. I lied. I am going to go back to what I was doing. Up here, that would be a 3x. And you got to think about it. I'm going to be taking it times another 3x, but I need more x's than that. To end up at an x to the 10th, I would have to have an x to the 5th and another x to the 5th. Because when I multiply that, I'd end up with an x to the 10th. And then what do you think your y's would have to be? What power? Well, it'd be a 6, because a y to the 6th times another y to the 6th, that's how you'd get your y to the 12th. Okay, so then when I'm doing this, the square root of this would be 3, x to the 5th, y to the 6th. All right, they might even throw a fraction at you. Something like this, square root of 64 over 9. They might even throw a negative out in front of it. That's okay. When you square root a fraction, you're ultimately just square rooting the numerator. So the square root of 64 is 8, and the square root of 9 is a 3. And then because of the negative that's out in front, that just makes my 8/3 negative as well. Okay, so let's do one more like this, but let's make it way fancier. I'm going to come down here where I have a little bit more space. Negative square root of 25 x to the 4th over 16 y to the 8th. Okay, take a minute to see if you can figure that one out. All right, it should be a negative out in front, and then the square root of 25 is a 5, and the x to the 4th is going to come from an x squared times an x squared. In my denominator, I do the square root of 16 and get a 4, and the y to the 8th is coming from a y to the 4th times another y to the 4th. There's my solution. Let's practice a few of these perfect cubes. So if you think of this one, so let's say you have the cube root of, I'll throw a negative out here. Let's make it be, I don't know, 27 x to the 6th, y to the 9th. All right, so first of all, I know it's going to be negative. And then I look at my number, the cube root of 27. Remember, I made my list over here on the right. That was a 3 times 3 times 3. That's how I got to the 27. So this is going to cube root to a negative 3. And then you have to think about this x to the 6th. Be careful here. This was an x to the something times an x to the something times an x to the something. And all of those need to add up to a 6. So that would be an x squared squared squared. When you're multiplying that, you end up at x to the 6th. So this is going to be x to the 6th. What do you think the y needs to be? So this would be a y to some power, y to the some power, y to the some power, so that they all add up to a 9. All right, hopefully that makes sense, that those would all have to be 3s. At 3, 3, and 3, that adds up to a y to the 9th. And so right here, that must have been a y. Oops, I wrote that wrong. Did you catch that? My bad. Let's backtrack. This 6 right here should not be a 6. We said up here that that was an x to the 2nd power, and then my y is going to be to the 3rd power. So it works sort of the same way, only now you're needing these numbers to, ultimately what you're wanting to have happen is to have this exponent right here and this exponent be multiples of 3, because you're just ultimately dividing it into 3 parts. Okay, let's try a fraction one, and then we'll move on. How about a cube root of, I don't know, let's try 64x to the 12th over a 125y to the 15th. All right, so what that would end up being, the cube root of 64, that comes from 4 times 4 times 4, so it's going to be a 4. The x to the 12th, if I divide it up into 3 parts, it would be an x to the 4th. My denominator, the cube root of 125, is 5 times 5, so that'd be a 5. And then a y, I have 15 of them, I got to split them up into 3 parts, it's going to be a y to the 5th. All right, let's take a look at a situation here where something might be negative. And I don't mean like the negative out in front of the radical, but the negative, let's say that it's tucked inside the radical. Let's say you had something like the cube root of negative 8. All right, so now you're looking at what is the number that you multiply by itself 3 times and you end up at negative 8. Well, I know 8 was really just was 2 cubed. So if it's negative, that's really just this going on. It was a negative 2 times a negative 2 times a negative 2. That ends up being a negative 8. So this is fine. That would end up equaling a negative 2, ultimately, is what that would end up equaling, negative 2. That's fine. So that worked out great. You just have to tuck a negative onto your answer. But let's see what happens when you do that with perfect squares. Let's say instead of a cube root, I was going to do a square root of a negative, let's make it negative 49. All right, so you might think that it's sort of the same deal. Oh, 49, that's 7 times 7. So it might feel like it's just a -7. But look what happens if you do that. If you were to actually take a -7 times a -7, you actually don't end up at -49. You would end up back at a +49. A negative times a negative would end up positive. So it doesn't really matter if you take a negative times a negative, or if you did a positive times a positive, there's still no possible way to end up with a -49. So what that means, and you could even try this one in your calculator, if you tried to take the square root of a -49, it'd give you some sort of an error message because there's not really a real number that would work to do that. So they call it a non-real value or something to that effect. So this actually isn't going to happen to us. Now, it might happen later in your math career, but it's not going to happen in this lesson. However, this one on the right, this cube root version, now that they might do. The whole trick is that there has to be 3 of them, or really it has to be an odd number of negatives. So it could, a 5th root of a negative would be okay. But over here, this square root would not work because if you have an even number of negatives, it's always going to go back positive. Okay, so one last time, if you have the negative out in front, if the negative is out in front, that's totally fine. Your answer just ends up negative. But if you're doing a square root, you cannot have the negative on the inside. But you can if it's an odd root, like a cube root. And we're only doing square roots and cube roots in this lesson. Okay, keep that in your mind. All right, so let's take a look at the situation where we're trying to take the square root of a number and it doesn't fall so perfectly into our list of perfect squares. Or I'm trying to do a cube root and it doesn't end up being one of these few numbers. All right, and of course, these lists go on and on. I've just given you kind of the top several before your numbers start getting very large. But I still am going to have a situation where, oh, look, I'm trying to take the square root of 20, and 20 is not a perfect square. All right, that's really, right here is the reason I gave you this list. Because what our goal is going to be then is to just try to reduce it. You want to have the smallest possible number tucked underneath this radical. And I bet you we could break this down into some smaller values that might get this 20 to be smaller. So here's sort of what our goal is. You're going to try to, you can multiply 2 radicals together and get, and build it back up to what you wanted. For instance, the square root of 20, I could break that down to the square root of 2 times the square root of 10. That would be the equivalent to the square root of 20. Okay, great. The problem is that doesn't really help me because what my goal here would be is to find some sort of number to put in here that is in my list of perfect squares because these are the only ones that come out clean. So I don't really want this 2 and 10. Could you think of some other factors of 20 whereas one of them would fall in my list of perfect squares? And I'm hoping you're saying, oh, well, that's easy. That would have to be a 4 and a 5. I write the square root of 4 because it's a perfect square and I know it's going to come out to a nice whole number. But I also have to have the square root of 5. That one's not going to come out nice. So then I take the square root of 4 and I reduce it as I can. It's just a 2, but the square root of 5 is going to say the square root of 5. And again, what our goal here was to get this, we call this the radicand. The number underneath the radical is the radicand. We're trying to get that to be as small as we can. And so this would be considered the simplified version of the square root of 20. Okay, so we're going to practice that a little bit. So let's try another one. Let's say you have the square root of 150. Getting a little bit bigger, but that's okay. We're going to multiply 2 things together to get 150. And I want to make sure that the first number that I write is something from my list of perfect squares. So you're looking, you're saying which one of these would, oh, I bet 25 would go in there. So it is 25. So 150, I think of it like money. 25 is like a quarter and this is $1.50. A quarter would go in there, let's see, 6 times. So 25 times 6 is 150. Now I chose 25 because it will square root into a nice whole number, but the square root of 6 has to stay there. All right, let's try some more. How about something like The cube root, we'll do a cube root one for practice here. The cube root of, let's say 54, and then just to make life interesting, I'm going to throw some variables in there also. Let's say, I'm going to do a whole bunch of them. Boy, I'm just going to power into a problem here. Let's see. And let's do z to the 10th. All right, this is going to be crazy. If you can do this one, you're going to be amazing. First of all, I'm doing a cube root, and 54 is not in my list of perfect cubes, so it's not going to come out nice. But I have to find one of these numbers that does go into 54. It happens to be 27. So I'm going to break this up into 2 of these cube roots. 27 times 2 actually gets me 54. I put 27 on the left because it's the part that's going to come out nice. I put the 2 on the right. I know that's going to get left. All right, so now I'm going to do the same thing with all of these exponent parts. Now you got to remember you're doing a cube root. So you got to think of this x to the 6th has to get split into 3 different chunks that are all identical. So that would work perfectly. So what I do here is I go ahead and I put the x to the 6th right here because it's going to cube root really nice. But remember when we did that, we always wanted that exponent to be a multiple of 3 because we're cube rooting, and the other 2 don't have that. This y to the 5th is not going to cube root nicely. To get a y to the 5th, it'd be something like a y squared times a y squared. Oh wait, I can only get one more y in there, so then they're not all the same. That's not going to work. So what you do is you pull as many of those out as you could so that it would divide nicely by 3. So if I have 5 of them there, I can only bring 3 of them over because I need this to be a multiple of 3, which means I still have 2 of them left sitting here. And there's my 5 y's that I had. So let's try that with the z. Same idea. 10 z's, that's not going to divide nicely by 3, but I bring as many of them as I can. So I'm going to bring 9 of them over. All right, so 9 of them will divide nicely, but that means that I still have one more that I didn't bring over, so it goes over there. All right, so then we go ahead and cube root all this first mess. So the cube root of 27 is 3. And then if I split that x to the 6th, I divide that 6 into 3 parts, it's going to be an x squared. The y cubed, when I split it into 3 parts, it's going to be a y. And the z to the 9th, split into 3 parts, it'd be a z cubed. That's what comes out as a nice whole number. The rest of this just stays in the cube root. One of the things you don't want to forget to do is to put the little 3, that's called the index number. The little 3 right here, that's your index number. When you're typing it into Hawks, if you forget to put that cube root, then it reads it as a square root and it's going to count it wrong. So, little detail. This is my final answer on this problem. All right, so now we're just kind of going to practice a few more of these, maybe try some more fraction ones. Let's see what we can do here. All right, so here's a few more. Let's just give them a shot, see how we do. On this first one, it looks like I'm doing a square root. Remember that this defaults to a square root when there's nothing there. So, and this negative out in front, remember that's totally okay when it's out in front. It's just going to be a negative answer. Now I'm wondering what you would do with this. I'm going to put a negative out in front, and I know I'm going to break it down to these 2 square roots. What's the perfect square that goes into 32? And if I had to guess, the first thing that comes to mind is probably a 4 times then a square root of 8, which is fine. That's true. That actually does work. The problem that we have, though, is that this 8 that's still tucked inside the radical is not as small as it could be. The square root of 8 actually reduces even further because 4 still goes into it. So now I could do 2 times, and now let's break down the 8. Square root of a 4 times the square root of a 2. All right, so now this, oh, and I lost my negative. Don't forget to do that. So then there's a negative 2 times, this first part became a 2, and then I still have the square root of 2. All right, and then these two 2's out in front can multiply to -4 root 2. And that is quite a heck of a process. Now, you can do that, and sometimes we do it. But you know what I would do? As soon as I chose this 4 and then I looked at the 8 and I think in my head, I think that'll break down again, I would have bailed on that whole mess. And I would have said 4 must not be the biggest thing that goes into 32 from my list. So let's take another look. Oh, you know what? 16 goes into 32. So really what you should have done is broken this down into the square root of 16 times the square root of 2. Then you have a negative. The square root of 16 is a nice perfect whole number. The square root of 2 stays put. And look what you got. You got the exact same thing as that, but way, way faster. So it is worth your time to make sure you have chosen the largest perfect square. Okie doke. Let's try again. Here's a fraction one. All right, so looking at this, I am doing a square root, so I'm over here looking at my list of perfect squares. I got lucky in the denominator. Look, I got a 49. That one's going to come out nice. But 40 is not in my list of perfect squares, so it's going to take some reducing. So here's how I would do that. I would break down the numerator into a square root times a square root. My denominator is just going to end up 7, the square root of 49. But the square root of 40 that's in the numerator, I'm going to come over here to my list and find the perfect square that goes into it. 4 obviously would go in there 10 times. And even though 10 seems like it's a pretty number, there isn't a perfect square that goes into 10. So I think I'm okay with just choosing 4 and 10. So then what I have is a 2 square root of 10 over a 7. Sometimes we get lucky and we can maybe reduce, like this 2 and 7 could reduce. You cannot reduce with something that's outside of a radical with something that's inside of a radical. That's not allowed. But in the end, nothing here reduces anyway. I'm good with what I've got. All right, let's try one more here. This one's a cube root. So now I'm over here looking at my list of perfect cubes rather than my list of perfect squares. So my list of perfect cubes, let's see. Well, again, I got lucky in the denominator because the perfect cube is already there. And remember, I also threw some variables here. You always want this power here to be divisible by this index. So since this is a 9, or since I'm doing a cube root, I want these to be divisible by 3. Again, lucky in the denominator, not so lucky in the numerator. So it's going to look similar to that one I just did. The top part, I'm going to have to reduce. I'm going to have a cube root of stuff that comes out nice times a cube root of stuff that doesn't. But in the denominator, that's a perfect cube as is. The cube root of 125, that's 5 times 5 times 5. So I would just write a 5. And then the x to the 9th, if I split those 9 x's into 3 groups, I'd have an x cubed for that part. Now in the numerator, let's work on that. A little trickier. I've got to find not a perfect square. Remember, I'm over here looking at perfect cubes now. I've got to find one of these numbers that goes into 81. You may find yourself kind of dependent a little bit on your calculator to find those. 81, actually 27 will go into that 3 times. So I'll put a 27 and a 3. But I also have this variable to deal with, this y to the 4th. Remember, I can pull as many over as long as they divide nicely by 3. So I can bring 3 of them over. I have to write small, sorry, that got tiny. I still have one of those y's left over. So the left part of this all cube roots nicely. The cube root of 27 is a 3. Cube root of y cubed, you just get a y. And then you have the cube root of 3y still left. And that is all over 5x to the cube, or cubed. And not super pretty, but mathematicians like it. I like it. All right, maybe you have the hang of it. I don't know. I'm going to give you one more slide of some practice problems in case you want to try some more. If you've got the hang of it, you can bail. I'm not tying you to this video, so it's just for your help. All right, why don't you give these two a shot, see if you can figure these two out, and then we'll call it good for a day. I'll give you a minute to try them. Go ahead and pause the video. Give them a shot. Then come back. Okay, spoiler alert. I'm about to give you the answer. Make sure you paused it. Here we go. This first one is a square root, so I'm looking for perfect squares. Oops. Perfect squares that go into 50. And then since I'm square rooting, I want these powers to be multiples of 2. All right, let's go ahead and break up into 2 different radical parts. What multiplies to get you 50? The first one has to come from your list of perfect squares. Should have had a 25 times a 2. And now I'm going to break these up. I'm doing a square root, so I got to bring over multiples of 2. That means I could bring over 2 of the x's. 1 is left over there. I could bring over 6 of the y's. 1 is still left over here. I could bring all of the z's over. And so then I'd have nothing left in the radical. All right, this first part comes out nice, the square root of 25, and then that's going to be an x. The y to the 6 split up over 2 parts would get you a y to the 3rd, and the z to the 10th split up over 2 parts. Again, you're doing 2 parts now because it's a square root instead of a cube root. All of that came out nice. This leftover just stays there, leftover. Final answer. All right, I'm going to go ahead and do the other one over here. Notice what happened here. I thought, oh, I talked about it, and then I didn't do it very often. Let's throw a negative on the inside. Is that going to work on this problem? And you're saying, yeah, sure it will work because that's odd. So it's okay for it to be negative. So let's give it a shot. Break it up into 2 cube roots. I get crazy with my colors, sorry. So this is the cube root that comes out nice. This is going to be the cube root leftover stuff. I look at my list of perfect cubes, figure out what goes into 40. 8 goes into 40. So then I've got, and actually I'm going to put in a negative 8 on that one. And then I put the 5 over there. All right, the x to the 7th I can bring over as long as they stay multiples of 3 because I'm cube rooting. So I'll bring 6 of them over. That one of them gets left there. This first part cube roots nicely to a negative 2x squared. And then I have the cube root of 5x left over in the didn't reduce pile. Okay, there you go. All right, hope this helped.